Okay, Chemistry 2330. I'm going to do our last section in chapter 12. It's reactions of aldehydes and ketones. So we learned this carbonyl gave us a bunch of different functionalities. We can attack it with a nucleophile because it's partially positive. We can create enols or acetals and hemiacetals to protect it. We can react it with Grignards, and we also learned in the last section we can use that eno-keto tautomerization to give us an alpha halogenation reaction. Well, let's talk about just the reactions at the carbonyl center itself. Okay, so one of the first things we can do with that, if we have an aldehyde, is that we can oxidize off this hydrogen to create a carboxylic acid. Okay, so the aldehyde is about halfway to the carboxylic acid, but not all the way. And so we can oxidize it a number of different ways. One way we can do it is using this chromic acid derivative, and it'll oxidize it to our regular carboxylic acid. Another way we can do it is just using oxygen or air. We can cause that aldehyde to slowly oxidize to a benzoic acid as well. So when we oxidize aldehydes, we get to carboxylic acids, okay? So most of the times ketones can't be oxidized, okay? But every once in a while, you can actually have it oxidize the enol form of the material. And what we end up doing is we end up oxidizing, breaking the alkene bond, just like we did in the alkene derivatives, giving us a dicarboxylic acid, okay? So it doesn't happen very often, but only when this enol form actually is formed in a high concentration can we get this oxidation to happen. But when we do form that enol in a high concentration, we can form a breaking of this double bond, giving us our dicarboxylic acid in the system. Okay. Another way to oxidize down aldehydes is to use a silver oxide and base. In the presence of the silver salt, we can take electrons away from the carbon and add them back to the silver, and therefore we end up oxidizing the carbon to a carboxylic acid and generating silver zero. When we do this, this is a reaction we can actually look at for a qualitative test for aldehydes, because what will happen is the silver will go from a silver salt, which is nice and brown, to actually producing silver metal on the surface of the glass, and therefore it's sometimes called the silver mirror test. We can actually see aldehydes oxidizing from their aldehyde form to their carboxylic acid form and leaving us with a nice silver mirror on the test tube. Okay, so what we can do is, instead of oxidizing, now that we can only oxidize the aldehydes and very rarely the ketones, let's go the other way. Let's take it and add hydrogen across the system. So aldehydes are always reduced to primary alcohols because we already have a hydrogen here that generates one of the hydrogens here, and we can add two hydrogens across that double bond to give us a primary alcohol. Ketones will always reduce down to give us a secondary aldehyde because we already have two R groups attached to the carbon, and we'll add one hydrogen to the carbon and one hydrogen to the oxygen. Okay, so we have a bunch of different ways we can do that. The first way we can do that is what we do, catalytic hydrogenation. Just like we reduce down a double bond, we can take catalytic hydrogenation with a metal catalyst like platinum or palladium or nickel, and we can reduce down the carbonyl to give us our secondary alcohol, okay? So if we have a combination of alkenes and carbonyl compounds, it will reduce both of them down, okay? So the catalytic hydrogenation reduces both carbonyls and double bonds. Therefore, you don't have control. You'll end up reducing all of those double bonds, both the carbon-carbon double bond and the carbon-oxygen double bond, down to give us to our, in this case, a primary alcohol. Okay. So if we want to be more specific and only reduce down our carbonyls, we have to go to reagents that are very specific and only react adding to the carbon and the oxygen of the carbonyl. And we have two good reagents for that. One is called sodium borohydride, and the other one's called lithium aluminum hydride. In both cases, the word hydride appears. The hydride, of course, is a hydrogen with a negative charge, so it has two electrons on it. And so it can use those 2 electrons to generate a new sigma bond, okay? And because it has a negative charge, it's a strong nucleophile and reacts on that carbon site of the carbonyl. Okay, so most of these are carried out in the presence of either water or alcohols, and that helps support it as a salt that can then be used to react with the aldehyde. Notice here it generates multiple aldehydes attack the sodium borohydride to transfer all of those hydrogens off, and then by adding water to the system, it breaks up the salts and gives us back our primary alcohols and some kind of borate salts. Okay. So let's look at that in a little more detail here. So what happens in the first step here is that we have a hydrogen transfer to the carbon of the carbonyl here. Then the oxygen of the carbonyl acts as the negative charge, and we end up with it creating a new oxygen boron bond. So this will do it multiple times with every single hydrogen on the sodium borohydride here. And then once we react it with water, that breaks this boron oxygen bond and generates our alcohol right here. So in the presence of a ketone, we get a secondary alcohol. In the presence of an aldehyde, we get a primary alcohol. Okay. So what if we wanted to only reduce down one versus the other? Okay, so if we had an alkene and the carbonyl compound and we used that catalytic hydrogenation, we would reduce both of the systems down, both the carbon-carbon double bond and the carbon-oxygen double bond. If we use sodium borohydride, the carbon-carbon double bond is untouched and we've reduced down our carbon-oxygen bond, double bond down to an alcohol. So what if we wanted to actually reduce down the carbon-carbon double bond and maintain our carbon-oxygen double bond? Well, that's when we have to go back to using it as a protecting group as the acetal. In this case, we're going to protect the carbonyl as our acetal. Again, it takes away that partially positive charge on carbon. It no longer reacts with nucleophiles. And then we can use our catalytic hydrogenation to convert our carbon-carbon double bond. And then by adding acid, we can liberate our carbonyl compound and we can generate this. So now we can do specific reactions on specific reactive groups. If we want to reduce both the carbon-oxygen bond and the carbon-carbon bond, we can use catalytic hydrogenation. If we only want to reduce the carbonyl, we have sodium borohydride and sodium aluminum hydride. Okay. If we want to reduce down just the carbon-carbon double bond, we have to protect the carbonyl as an acetal, do our reaction, and then break the acetal, reliberating our carbonyl compound. All right, this is the summation of our carbonyl compounds. We've done a lot of different work with those, and knowing that this is a nice polar bond with a partially positive side here and a partially negative here gives us our reactivity